All right, welcome to the Explainer. Today, we're going to dig into something pretty fundamental, probability. And we're going to challenge the very first thing you probably ever learned about it. Turns out there's a single hidden rule that changes, well, pretty much everything. So let's kick things off with a kind of provocative question. You know that first formula you ever learned for probability? Favorable outcomes divided by total outcomes? Yeah, that one. What if I told you it's, well, dangerously incomplete? Like, it has this one hidden flaw that if you don't know about it, can lead you to answers that are just plain wrong. So here's the game plan for today. We're going to take a little journey through 4 key ideas. First, we'll uncover that hidden rule I mentioned. Then, we'll get into how to shrink the world of possibilities. After that, we'll look at the ultimate test for independence. And finally, we'll put on our detective hats and use probability to work backward. All right, let's jump right into part 1, more than favorable over total. This is where we uncover that hidden rule. Okay, so this is probably burned into your brain, right? The classic definition of probability. It feels so simple, so intuitive. But here's the catch, and it's a big one. It only works if one crucial, and I mean crucial, condition is met. A condition that honestly gets forgotten all the time. And believe me, that one condition is everything. So let's put this classic formula to the test. Here's a problem you might see on an exam. Think about this for a second. We toss a coin. If we get heads, we just toss it again. But if we get tails, we switch gears and throw a die. The question is, what's the probability the die shows a number greater than 4, given that we know there's at least one tail in the outcome? Okay, so if you just use that simple counting method, the logic seems pretty straightforward. You'd list out all the outcomes that have at least one tail, right? That gives you 7 different possibilities. Then you just look for the ones we care about. The die showing a number bigger than 4. That's just T5 and T6. So 2 favorable outcomes out of 7 total. The answer must be 2 7ths. Seems easy enough. But that is completely wrong. And understanding why it's wrong, that's the real secret to getting a handle on probability. And here it is. This is that hidden flaw we've been talking about. That simple counting formula only, and I mean only, works when every single outcome has an equal chance of happening. But in our little experiment, they don't. Think about it. The probability of getting heads then tails is a half times a half, which is 1/4. But the probability of getting tails then rolling a 1 is a half times a sixth, which is only 1/12. These outcomes just aren't the same. They have totally different weights. So what do? How do we fix this? Well, since we can't just count the outcomes because they have different weights, we have to do something else. We have to calculate the actual probability for each and every path and then add them up. So for the thing we want, our favorable event, we add up the true probabilities of T5 and T6. And for the condition we were given, we have to add up the true probabilities of all 7 of those possibilities. And when you do all that math, a very different answer pops out. The real answer is 2 9ths. Now, you might look at 2 7 and 2 9ths and think, they're pretty close. But the difference in the numbers is tiny compared to the massive difference in the logic. This is the big takeaway. Before you ever just start counting outcomes, you have to ask yourself, are they all equally likely? If not, you got to switch gears. All right, let's move on to our next big idea, shrinking the sample space. This is all about how a single piece of new information can literally change the entire world of possibilities. You know, whenever you're reading a probability problem, I want you to look for these signal words, phrases like given that or if it is known that. When you see those, a little alarm bell should go off in your head. Ding, ding, ding. That's your clue that you're dealing with conditional probability, and the universe of outcomes you're thinking about is about to get a lot smaller. Okay, let's look at an absolute classic problem here. I mean, this one trips up so many people, it's almost a rite of passage. It sounds simple, but it is the perfect way to understand this idea of a shrinking sample space. So first things first, we have to map out every single possibility, the full sample space. And here's a super important point. Order matters. Having an older boy and a younger girl is a totally different outcome than having an older girl and a younger boy. So when you list them all out, you get 4 distinct, equally likely possibilities. Okay, now here's where the magic happens. We get a new piece of information, a condition, given that at least one child is a boy. This new fact acts like a filter. It instantly tells us that one of those 4 outcomes we just listed, well, it's now impossible. We just take the girl-girl scenario and toss it right out the window. It can't exist in our new reality. So just like that, our entire world of possibilities, our sample space, has literally shrunk from 4 options down to only 3. And that right there is the heart of conditional probability. We're not in the old world of 4 outcomes anymore. We're operating in this new, smaller world of just 3. And in this new world, how many outcomes match what we're looking for? Both are boys? Just 1. So the answer is 1 out of 3. Simple as that. So, we've seen how knowing one thing can change the odds of another. But what if they don't affect each other at all? How can we be sure? Well, there's a super simple formula that acts as the ultimate independence test. Let's check it out. Forget all the complicated definitions you might have heard. This, right here, is the only test that matters. It's the ultimate litmus test for independence. Does the probability of A and B happening together equal the probability of A times the probability of B? Think about it. Rolling a die and flipping a coin. The chance of rolling a 6 and getting heads is 1/6 times 1/2, which is 1/12. The math works. They're independent. If that equation doesn't work, well, then the events are dependent. It's really that simple. All right, for our last section, we're going to get into what I think is one of the most powerful and, frankly, coolest ideas in all of probability. We're going to learn how to become a kind of statistical detective, using Bayes' theorem to work backward from an effect to find its most likely cause. So imagine a factory with a few different machines making light bulbs. Calculating probability going forward is pretty easy. Like, what are the odds that we happen to pick machine E1 and that machine then produces a defective bulb? That's simple, right? You just multiply the chance of picking machine E1 by its known defect rate. But that's not usually the question we have in the real world, is it? The real question is backward. You're standing there holding a defective bulb in your hand. That's your evidence. Now you have to figure out what's the probability it came from machine E1. See? We're working backward from the evidence, and that's exactly what Bayes' theorem is for. And honestly, when you strip it all down, Bayes' theorem is surprisingly simple. It's really just a fraction. The top number, the numerator, is the probability of the one specific story you're interested in, so the chance that the bulb came from machine E1 and was defective. The bottom number, the denominator, is just the sum of the probabilities of all the ways you could have ended up with a defective bulb, whether it's from machine E1 or machine E2 or any other machine. Okay, to bring all these ideas together, let's look at a really cool question about fairness. Imagine a hockey match is tied. To decide a winner, the teams are just going to take turns throwing a die, and the first one to get a 6 wins. Team A gets to start. Now, on the surface, that seems totally fair. It's just a random die roll. But is it really? Well, when you actually sit down and run the numbers, using the rules of probability, something pretty shocking comes out. Team A, just because they get to go first, actually has a 6 out of 11 chance of winning, and that means Team B only has a 5 out of 11 chance. It's not a 50-50 coin flip, not even close. And that really brings us to the final point. Probability isn't just about crunching numbers for an exam. It's a powerful lens. It lets you see the hidden biases and unfair structures and systems that we all just assume are perfectly fair. This little die-rolling game proves that even when something is based on pure chance, the rules themselves can create a hidden, measurable advantage. It really makes you stop and think, doesn't it? What else out there that we assume is fair isn't fair at all?